put the microphone?
So thanks everybody for staying so late in this workshop. This is the last session. It's not the last talk, but it's the last session of the workshop. And it has been amazing to have you all here online and in person. So it is my pleasure to introduce Otavio Bueno, who, as he was saying in the talk before, he doesn't need any presentation, but he has been working, before working on understanding, he has been working on structural features in science and how theories represent, and he also has worked on certain parts of logic and set theory, so he works all over the philosophy of science field, and it's a pleasure to have you here. So you have something like 40 minutes. Yeah. I'll let you know when you have spoken for half an hour.
Okay, thank you. Well, thanks, Maria, for the invitation and for organizing such a terrific workshop. And so it's always a pleasure to come back to Mexico City, and UNAM in particular. So, I'm going to talk about a particular kind of scientific understanding, right? And as it will become clear, modality plays an important role in the story and structure as well. We're going to see how those things play out, right? And I'll start with often a point that we've made already in the conference, right? Ways in which scientific understanding depend on an account of explanation, right? And typically it's the result of explanatory practices in the sciences that we get some form of intelligibility. Direct account is like that, right? And interestingly, Peter Lipton, a long time ago, argued that we should not do that, right? That understanding should be understood and characterized in a broader way than explanation, right? And I think he was right in making this point. And what I'm going to do is to build up on that insight, right, and offer a way of thinking about scientific understanding that does not depend on explanatory relations, right? And of course, it will depend on something else, right? Of course, I'm not offering a definition of understanding. I don't think you can offer a definition of understanding that does not presuppose some form of understanding, illumination, or something like that. So I don't think understanding is that kind of thing. In any case, I'm interested in giving the structure of the kinds of connections between phenomena and models in the sciences that will deliver some form of understanding, right? And so I'll give an example. Throughout the talk, I'll give several. One we'll work through a little bit, the Lochner-Voltaire equation and how it can represent the phenomena in a variety of ways, right? And as I'll become clear, central to the account here is this idea of structure preservation, how you move structures from one domain to another as a central aspect of scientific practice, right? And a central aspect of what allows scientific phenomena to be understood, right? So recognizing a same similarity of patterns across a diversity of phenomena is one way in which you can understand them, right? What I'll try to say is that we can have that without having an explanation, right? Not that it cannot. There are cases in which understanding does come out of explanations, right? But it need not, right? And and I think in doing that, it will be more transparent what the relations are between modality and understanding, right? And ultimately, I do think that scientific understanding is a form of modal reasoning. And towards the end, of course, this is a view that has been defended for people here in the audience, and so which I'm very sympathetic with, right? And I'm going to, along the way, indicate some of the differences, right? So I would say that this, with Soazek, the difference is it's a family divergence, right? So we agree on the basics, right? We may disagree about some of the details. So, okay. So now, if you think about traditional models of scientific explanation, right, the deductive nomological account, the unificatory model, the pragmatics of explanation, all of them offer understanding as, here, something you can get for free, right? Once you have an explanation, you can, it's because you're explaining the phenomena that you're understanding it, right? So, and on these views, independently of how we characterize an explanation, right? In the deductive nomological account is an argument, from laws and initial conditions to what has to be explained. In the unificatory account, it's sort of identification of overall patterns, right? Or answers to why questions in the pragmatics of explanation. In any of those, you do get understanding as a byproduct of explanation, right? And so I don't deny that there are cases in which that does happen. So what I'll take issue is that that's the only route, or even the most important route for scientific understanding. Right? And why is that, right? So, and that's one of the insights that Peter Lipton had, right? So it says, well, maybe we should think about understanding as something that it stands on its own, right? That it's not an afterthought from explanatory practices, right? And I think that should be the most important insight of this 1909 paper of his, right? I disagree with Peter about a lot of things. I'm not a scientific realist. I don't think inference to the best explanation is a good form of reasoning. So we disagree with tons of things. So I'm not going to bring all the tools that he has. I'm bringing the point that he made, right, which I think is exactly right. Now I'm going to work this point in my own way, right? And because I think there are ways that they can illuminate certain things as a result, right? So I'm going to give an example here to illustrate the point. It's not something that Peter did, so I'm just lifting one page, right, of that paper, and then the rest you can blame on me, right? And so a couple of differential equations that are very good at describing the covariance between two magnitudes, right? And one way in which those equations have been used is to think about in ecology how and the growth decreases. And as it decreases, well, then there are less easily available food around, and then there is a decrease in the predators. Well, with that decrease, got back to the whole process again, because then more food around and so on, right? So now, first, it's a very idealized model, right? There are a bunch of assumptions that get built into this model, namely, predators only eat their prey and nothing else. They have plenty of it, right? Nothing else is interfering with them. So you have a bunch of simplifications that we know are not actually right, right? So you get this, elegant sort of cyclical pattern, right? The actual data, would look something more like this, right? And that's something that often happens in the sciences, right? So you can see that the pattern is, oh, okay, it's more or less. Yeah, there is some cyclical, but it's not just as neat, right? So once, the idealizations are not in place, what you have is just a general pattern, right, going on. What is interesting, however, what we get here from a purely mathematical point of view, if you look at the two differential equations, right, all you had is just a correlation between these two variables, right? And and as a result, you actually don't have an explanation, right, of the phenomena, right? What you have is you have a representation of it, right? So the little model that I show represents how that cyclical pattern goes on. And I think it does give us some understanding about the connections between these variables, right? But it doesn't explain, right? Certainly it doesn't explain alone, right? If you think about, just by looking at the pattern in that I showed a minute ago, right? You say, okay, now I explain, right? It'll be very surprising that you get an explanation here, right? What you have is just a representation of of a phenomenon. I think you do get an understanding. You can see how the two magnitudes are covariant, right? So I would say that what we have is a description, right, rather than an explanation of the relevant phenomena, right? So, and now, if you want to get an explanation, you need something more, right? Typically, the explanation would need to identify factors in the phenomena itself, right? The fact that predators are actually eating, being eaten by eating the prey, right? So there are causal connections between the relevant things. That's what explains, but that's not what the model gives you, right? So it's in that sense that what the model gives you is just a correlation between these things, and it's a form of understanding, right? So the point would be similar. So if you say, look, I have this clicker here, right? So if I throw it up, eventually it's going to come down and crash on the ground, right? So, and you may say, okay, why is it that after a while it came down? And you may say, oh, look, here's the equation describing the motion of this thing as it went up. And at this point, the value of that equation was 0. That's why it came down, right? If you say that, you say, well, have I explained the phenomena in doing that? I would say, no, you didn't. That equation would describe the phenomena, right? That's the point in which, the velocity is 0, and then slowly the force will start acting. What explains are the proper gravitational relations. The force is acting on those things. That's where the explanation is, right? But the equation does give us some understanding, right? The equations give, in fact, the conditions under which this thing will go down, right? We say, well, we have the forces acting on it described in this way, right? So the thought is, a mathematical model alone may give you some understanding, but will not give you an explanation, right? An explanation often will have additional constraints, but it can give you some understanding about the overall patterns involved in the phenomena. Okay, so that's the idea, right? Now, what kind of understanding is involved here, right? So the thought is, what you have is, there are particular structural configurations, right? So we have a phenomena in the world, right? And the predators in place. I have a certain mathematical model, right? The equations, the differential equations that describe correlations between magnitudes. And what we have is a way of mapping one into the other, right? And identifying similar patterns, similar structures between them, right? So what the Lotter-Voltaire equation does is to give us a particular structure, a particular mathematical configuration, highlighting the correlation between these magnitudes, right? As a piece of pure mathematics, the equation doesn't say anything about the world, right? The equation talks about functions, numbers. So those things have to be interpreted before it can say anything about the world, right? Once the equation is given a particular interpretation, then it associates increases and decreases of values of functions in the model with the growth and decline of the corresponding population size, the population size of predators and prey in the world, right? Once you have that interpretation, right, then you have something, right, that can give you some of the relevant understanding. So here's the idea then, right? You have some empirical phenomena, right? You immerse selected features of the phenomena into a mathematical model. So immersion, right? That mathematical model has some internal structure, right? You derive consequences from that structure, right? And then you interpret the results back in the world, right? And what we have is a sort of an inferential conception, right? About the ways in which models can represent phenomena, right? So that's the simple account, right? You have some empirical phenomena. So you may be interested in the population, right? The predators and prey. You have a couple of differential equations that describe a cyclical pattern, right? You map selected features of those objects into the model. You solve the equations, right? And then you interpret the result back in the world as saying something about how is it that that cycle would go over time, right? Now, note that connecting a mathematical model with an empirical setup via maps and interpretation is quite different from just explaining the phenomena by embedding the phenomenon into a broader unified pattern. Right? The reason is because you may have a model, a mathematical model that is broader and unified, right? But it's not required to be used to represent the relevant phenomena, to provide understanding, right? So usually, explanation by unification has additional constraints, right? That the model may not have, right? So we can understand the result quite independently of any unification that the model may provide, right? So understanding of the account suggested here emerges from the interpretation, right? From indicating how the mathematical structures can be connected with the empirical setup, right? So you identify this class of phenomena in the model and interpret them back into the world. Well, that's when you're getting an understanding, right? Now, what this understanding gives us is actually something modal. It gives us a way in which the phenomena could be, right? It represents a possibility among the various connections in the world, right? So in this way, the scientific understanding is a form of modal representation and modal reasoning, right? You're reasoning about possibilities about the phenomena being guided by the model, the mathematical model, right? So in a way, so it indicates configurations about how the way the world could be given the mathematical model, right? So the intertwined relations in the populational growth of predators and prey displayed in a suitable interpreted Lockyer-Voltaire equation indicate how the variations could be in the world, right? That's where the modality comes in. So in that sense, scientific understanding has a significant modal content. It's about the possibilities in the phenomena, right? So scientific understanding, making sense, accounting for how certain situations could be, are all intertwined on this approach, right? So the resulting understanding derives from the structural relations among the phenomena and corresponding and suitably interpreted mathematical structures. Now, this is one way in which mathematical models can be used then to illuminate the relevant phenomena. Now, I want to say that this is a particular way, right, of scientific understanding. It's a sort of a structural form of understanding, right? Highlights the role that those structures are playing about the possibility of certain empirical configurations, right? Now, are there criteria for scientific understanding that are not criteria for explanation, right? And I want to say that there are, and that's why the two things can come apart, right? You may have something that gives you understanding, even though it may not explain, right? So here's one, embeddability, right? So in the sciences, understanding a phenomena typically involves a form of embedding the phenomena in a properly interpreted mathematical structure, right? That's what I just did with the immersion and then the interpretation back, right? So the understanding emerged from the realization of what makes the phenomenon possible, given the configurations in the model, right? The model highlights the possibilities, right, that are then interpreted back in the world, right? However, the embedding is not necessarily a form of explanation, right? As structures can be embedded into another without any explanatory gain, right? So usually unification accounts of explanation require more than just embedding, right? So, to get the explanatory relation. So for example, you can embed the odd numbers structure into the structure of natural numbers, right? It's easy to do that. Does that give you any form of explanation? No, right? But it gives you an understanding, right? It gives you an understanding about how these structures are related, right? It gives you a form of conceptualize what's possible or not to do with them. The second way in which something may give you understanding without an explanation, right? the idea of scientific representability. And in the science, representing a phenomenon often provides some understanding. That's one way you can understand a phenomenon, is by representing into a certain structure, right? So again, the examples I gave of the Lotka-Volter's equation, representing possibilities in the phenomena, right, by a mathematical model, right? Now, often in the sciences, the information you have is partial, right? You know that certain relations hold, you know that other relations do not hold, and a bunch of them you just don't know whether they hold or not, right? So you have at best for the partial relations, right? Partial representations of those things. And they are often exploited effectively by scientists, that partiality, right? So here's an example I love to give, right? Dirac's equation, right? So in the late 20s, Dirac came up with a differential equation that we now call Dirac equation. And that equation had negative energy solutions, right? And he immediately response was to say, well, we're going to treat this equation, the solutions, just as we treat negative solutions in classical mechanics. They don't mean anything. They are artifacts of the mathematics. Ignore them, right? 2 years later, he came back and said, no, I spoke too quickly, right? These negative energy solutions stand for holes in the space-time, right? So he gave a physical interpretation to those features of the mathematics, right? We are in the bottom of the representation device, right? The interpretation part, right? He had the equations there, getting these negative energy solutions, and he was now finding a way of interpreting them back into the world, right? Now, this idea of the holes in space-time, immediately Heisenberg and Weil pointed out to him, to Dirac, that according to this whole interpretation, protons and electrons will have the same mass. And that's just empirically wrong, right? Okay, forget it. Undeterred, 2 years later, Dirac comes back and say, all right, forget about the whole theory. Here's what's really happening. These negative energy solutions stand for a new particle that has exactly the same mass as the electron, but the opposite charge. The idea of the positron was created, right? By how? By interpreting a particular mathematical structure, right? 2 years later, Anderson, messing up with his instruments, found something that with a lot of work you can reconstruct as evidence for that particle, right? What's interesting for us here is the following, right? The same equation, the same differential equation is compatible with 3 entirely different interpretations. One in which the equations mean nothing, one in which it means something that it's empirically false, and another one in which you found a new particle out of it. It's the same equations, right? So there's a sense in which the mathematics is offering a space of possibilities, right? And what Dirac is doing is exploring these possibilities, right? Trying to find among these mathematically possible things, which of them may correspond to something physically real. And that's what the interpretation part comes in, right? So he was representing the phenomena, right? He was representing 3 different ways that the phenomena could be, right? And they are incompatible among themselves, right? But compatible with the same mathematical equation. So the equation itself only shows how things could be. That's all we can do. The interpretation bit is where then you ground that with the empirical phenomena, right? So I want to say that the equation gives us some understanding. It gives us exactly the possibilities. And what Dirac was trying to do is, among these possibilities, can I narrow it down to one in which I can give something that it's empirically testable and not empirically false, right? And that's what he did, right? So now that's one way, right? So you may use features of the mathematics as having surplus structure, right? So they offer extra things that you can reinterpret in creative ways. That's a way of offering understanding, right? Even if you're unable to explain, right, the things. In fact, Dirac didn't even know what was it that he was trying to look for, right? In fact, even the prediction of the positor could be false, right? So You have to be lucky as well, right? But in other cases, right, so you abstract away from the structures. And I think in the Lockyer-Volterra case, that's what happened. Right? There are the phenomena we are trying to make sense in the world, the relations with the predators and are far more complicated than the two tiny differential equations capture. So we drastically idealize, simplify the phenomena in doing that, right? So in other cases, the structures offer some additional information, right? And so here's another kind of representability, right? That's also central in scientific practice with microscopy, right? Often you get data from microscopes, say atomic force microscope, that gives you information about the surface structures of some sample. But that structure is not fine-grained enough to give you all the tiny relations among the various objects. So what do? Well, you do what Descartes said you should do in the principles. With regard to the things you cannot see, it's enough to say how they can possibly be, right? You make something up, right? And that's what you do. And microscopists do that regularly, right? So this is, scanning of a surface using atomic force microscope. It gives you information about the surface of a carbon structure, right? And you have the configuration among the relations about the various atoms in it. And if you think, so you recognize the hexagon here, right? So what the instrument cannot resolve is what's the structure among these tiny little atoms, right? It cannot because the tip of the microscope, it's actually the sharpest possible tip. It's a single atom. So it's too big to resolve, things below the atomic structure. So you cannot, even though when Rory and Binnick, who invented this instrument in 1986, they won the Nobel Prize in Physics. And in the description of the phenomena, the Swedish Academy tells us now we can see atoms, right? Well, we cannot see atoms, right? Because atoms are too big for them to be seen. But we got a fairly good representation of the surface of all kinds of atomic structures. But there are lots of things about the relations among these atoms that we cannot resolve and could not possibly resolve with an instrument like that. So what do? You say, okay, here are the 6 atoms, here are the possible configurations. So you add something to them about a possibility. You're adding some structure there to give some interpretation. It gives some understanding. Again, a modal understanding, right? It's telling you how things could be, given the empirical information that the instrument is giving us. So in both cases, this and in the previous example, understanding is increased by indication possibilities in the phenomena. Even though in none of these cases, an explanation provided by the mathematical model alone is forthcoming. Right? The mathematical model doesn't explain those things. It gives you a configuration about the possibilities, the possible relations among the phenomena, but not why they are that way. Right? But I want to say, we do give, look, the micrograph gives us a structure that helps us understand a possibility among the complex interactions among the bonds among these atoms. All right. So just as a representation can be more abstract or more specific than the various objects in the investigation, the same happens with the corresponding understanding. So one embeds the phenomenon into a richer structure, which allows the identification of connections among the relevant objects. So sometimes embedding, so people who believe, for example, that there are mathematical explanations, right, would say, well, by embedding some structures into larger ones, we can understand, right? And more than that, we can explain why is it that certain things hold, right? So for example, Mark Olivan argues that kind of embedding, so if you add, so you have differential equations, right? They have solutions all over the place, right? If you embed that space of the solutions into a space of complex numbers, right? Suddenly, what appeared to be scattered solutions all over the place found a unified pattern, right? So there's some extra structure given by the complex numbers. he wants to say, oh, now that extra structure given by the complex number explains that pattern, right? I want to resist that explain. There is an explanation here, right? I want to say what we get here is a form of understanding. I know how these two structures connect. An apparently gerrymandered structure of solutions of differential equations, and if I embed this into a larger structure, I can see a pattern that I couldn't see otherwise. Am I explaining it? No. What I'm doing is I'm showing how, by embedding this apparently gerrymandered structure into a larger one, a larger pattern emerged. So that gives me an understanding. I don't think it gives an explanation, because it doesn't tell us, why is it that the embeddings have the properties they do, right? They just give me the embedding. But the embedding gives me an understanding about why is it that what apparently was gerrymandered all over the place actually has some overall unified pattern. Now, the final part. So I think everything that I said would fit very nicely with Soazig's approach of the modal understanding, right? So she highlights, I think rightly so, the role of modality in understanding. She's offering a modal account, right? And of course, central for her account is the notion of a possibility space, right? And the 2017 paper, she tells us, one has a modal understanding of some phenomena if and only if one knows how to navigate some of the possibility space associated with the phenomena. So understanding here is characterized as a form of know-how. It's a know-how of, so knowing how navigate this possibility space. And what is the possibility space? Well, the notion of possibility space is meant to be comprehensive. First, we consider the set of possible worlds in which P, or some subset of P, which P is a fixed domain of phenomena, is the case. So we have some phenomena I'm trying to make sense, right? I'm going to fix that, and then I'm considering the set of possible worlds in which this phenomena obtains. Next, we consider the set of dependency structures that, when appropriately associated together, give rise to the phenomena, or to some parts of the phenomena within this set of possible worlds. The possibility space for the phenomena will be the set of dependency structures in those possible worlds that give rise to any subset of the phenomena and the relations between those structures. So what's important here, right, is the idea that, look, we have the phenomena, but also we have all the relations among these phenomena, the complex network, right, of relations that are captured in this set of possible worlds, right, in which the phenomena holds, right? Okay, I think the focus on modality is exactly right, right, and we are on the same page. So that's a central feature, right? So I think where I would disagree, and this is, as I said, it's probably a family disagreement more than anything else, right? Two concerns, right? One is with the identification of understanding with know-how, right? I worried about that, and why is that? Well, knowledge, even know-how, is a success term, right? And we may have understanding even without knowing how to navigate the possibility space. In fact, the example I gave of Dirac, I think, is exactly like that, right? He did not even know what the possibilities were. He was trying to figure out as he went along, right? After the fact, we could look and say, look, you have, in fact, after the fact, it's very easy. Often people describe the discovery of the positron like this. Isn't it amazing that Dirac, by looking at the shape of a differential equation, uncover a new particle in the universe? Yeah, if that's what happened, it would be pretty amazing, right? The story I told you is actually the way in which that discovery took place makes clear that that was not what happened, right? He was trying out. He was figuring out what are the possibilities. So he did not know what the possibility space was, right? That was part of the problem. You need to find out, right? There were too many possibilities for him to navigate, right? The second concern is with the use of possible worlds to characterize the space of possibilities, right? I would resist that. I think possible worlds are a terrible way of doing modality, in large part because not every possibility can be characterized in terms of a possible world, right? They are too restricted, right? Think about what Leibniz and Newton were doing in the 17th century when they were developing the calculus, right? So they introduced this notion of infinitesimals, right? So this is a it's positive magnitude that's smaller than any positive number, right? So now, because it's positive, it's different from 0, right? So you can divide by it. Then you divide by it in your calculations, and then you end up with some infinitesimals at the end of the calculation. And then you say, well, because this thing here is smaller than any number, well, it's 0. Get rid of it, right? So you treat it as being both different from 0 and identical to 0. The thing is inconsistent, right? Amazingly, it works, right? Doing exactly this thing, both Leibniz and Newton gave exactly the laws of differential calculus that we use to this day, right? In a completely inconsistent basis, right? I want to represent what they were doing. I cannot do that in any possible world, because what they were doing is reasoning about an inconsistency throughout, right? And thinking of the world as having those things in them, right? So I would say we don't need possible worlds, right? So here's a different way, right? I like to think instead of thinking about possibility space, think about a logical space, right? The space of all possibilities, where don't think about possibilities as what's true in a world. That's a bad way of thinking, right? In fact, we cannot define possibility in a way that does not invoke modality. Not even Lewis can do that, right? Because Lewis says, look, what's possible, what's true in a world, right? And what's necessary is true in every world, right? So you think about the structure of the logical space itself, and you say, why is it that in that structure, there's no inconsistency? Why there's no contradiction anywhere? So, well, because these are the possible things, right? So only possibilities are supposed to be represented there, right? But to do that, you need to have a notion of possibility that is not world-bound, because it gives you the very structure of the logical space. And so you need some possibility. So even Lewis needs a primitive notion of possibility. The modalist says, well, so embrace that, right? Recognize that you cannot define modality in non-modal terms and work from there. So there is a space, there's a logical space. What will happen often is the logical space, we are not aware of all the structure that space has. There are possibilities that sometimes our own logics preclude us from recognizing, right? Classical logic would say you cannot reason without triviality on the basis of an inconsistent theory. That's impossible to do, right? But there is that possibility in the logical space. It's just that it's not one recognized by classical logic, right? A paraconsistent logic will do that, right? And you can think about the logical space as a space of all possibilities, really all, not just possibilities given a certain framework, right? And we don't know all the structure that there is there. It's something that we need to find out, right? And so that's the way I prefer to think about what's possible, right? And I think we get different logics dropping out of those things by exploring different regions of the logical space, right? And then we can even talk about Swazig's idea of the trajectories in the logical space. I think that's something that Dirac was doing, right? He was trying to figure out what, among the mathematically possible alternatives to the Dirac equation, what among those had physical meaning, right? So in this way, you can allow for representations of inconsistencies involving understanding, which I think is what happens with infinitesimals, right? And does not require knowledge, even an ability-based one such as know-how, underlying the approach. So we don't need those two features, right, if you have this modalist account of logical space, right? So to conclude, scientific understanding, structural mappings, and modality, I think are all closely connected, right? Even though in many cases explanation does provide understanding, especially if the explanation is not too complex, gerrymandered, or convoluted to illuminate the phenomena, understanding can be reached independently of any explanatory route. So I think it's better to separate these two things. So briefly indicated above are some of these routes, right? By embedding, via representing the relevant phenomena, right? These are possible ways in which we may have understanding without necessarily having explanation, right? And I think, even though this is just part of the logical space, it's something that I hope it's worth exploring further. Thank you very much.
Thank you so much, Otavio. I love your paper.
Thank you.
So I think that you're absolutely right. And so here's actually a suggestion to bring more grist to your mill. So, I mean, I love the fact that you picked the Lotka-Volterra equations as basically your example. But I think that what you presented generalizes to basically other things. And what I have in mind in particular is Nash equilibria. Because Nash equilibria can be applied in a variety of different disciplines. For instance, in the case of biology, you have basically evolutionary stable strategies, which are basically a refined version of Nash equilibria, which provide you with basically an understanding of how certain species can evolve in certain ways without telling you why they're evolving basically in specific ways. And the same thing applies basically with other disciplines where you have refinements of basically Nash equilibria, for instance, in traffic flow control. You basically have applications basically of Nash equilibria, which tell you basically what possible routes people can adopt without telling you why they're following a particular road.
Perfect. I completely agree with you. And so, yeah, of course, the hope is that this can be applied to a variety of aspects of scientific practice. And you're quite right. Nash equilibria is a really interesting case because it's also navigate across different phenomena. So it's perfect. I fully agree. Thank you.
So, Dave, did you raise your hand like that?
Yeah, no question. Yeah. So just a small comment on the prey predator thing. So it seems to me what gives you understanding here is when you realize just the fact that it's realizing or grasping that the more predators there are, the more efficient it'll be at killing the prey, and that will tend to drive the number of preys down, and and then the other direction. But that is not part of the differential equation.
That's correct. Yep.
That the differential equation is purely structural, and you say, well, that constrains the possibilities, but the fact that I'm describing, like the fact that was just describing, is something above and beyond, and is kind of what explains why the differential equation characterizes the fluctuation of these populations.
Yep.
So it seems to me that you seem to be agreeing, but I thought I was pointing out that your picture is kind of incomplete. When you say, like, the understanding is given by the differential equation and structure, and now that shows you the space of possibilities, I want to say no. The understanding is given by the more basic fact, which predicts that the possibilities the space of possibilities is such as is described by these equations.
Okay, so they're two different things, right? So what I want to say is to give an explanation, right, of what's happening, you need to have the relevant causal factors in place, right? It's the fact that the predators are eating the prey, right, in that way, right? And so what the differential equations give is just a pattern, right, of correlation between these magnitudes, right? Now, the pattern, if you think, okay, I'm now interpreting these magnitudes as standing for the growth of the population, right? When I do that, I do have some understanding, right? Even if I don't have quite the mechanism, right? The mechanism requires some knowledge about what the predators are actually doing, right? Because all the model is giving me, even interpreting in terms of growth of predators and prey, is just this correlation between these two things, which is a form of understanding. But not an explanation.
It leaves the whole thing. It isn't mysterious. Like itself is mysterious and leaves everything mysterious unless you grasp the mechanism that explains these predicates.
Explain,
Yeah.
right? So I think you have an understanding there without the explanation, right? The explanation will require identifying the relevant causal factors, right? And then of course I do have an explanation, right? But I think before I have that, I do have an understanding of how the two things are, what the model gives us when you interpret the model in terms of there's a correlation between the growth of these two populations. Now I have an understanding of the connection between these two things.
Understanding of why. Like you said, understanding how, but understanding why the complex phrase like this requires.
That's right. I agree with that, right? But because that's understanding why there is actually explaining, right? And that will require more than what the understanding.
So we are going to take a question from Zoom. Maxime, can you open your mic, please?
Hi, Otavio. Thanks for the great talk. So my question is related to the last one. So I was wondering, what is your view on explanation, since you make emphasis to distinct your understanding with explanation? For example, there are people who also talk about how possible explanation, which is also seems like quite related to modality. And you also mentioned that your view, and also with another author, understanding is about grasping the kind of dependency relation in the possibility space. That also seems to be quite closely related to explanation.
Yeah. Great. So of course in this kind of explanation, right? So I am articulating a notion of understanding that need not depend on explanation, right? And so I'm sympathetic with the pragmatics of explanation that Van Frassen develops. So I don't think it offers the full picture. So for example, it's not clear how to apply it to mathematical explanations, for example, right? Given the way that the model is set up. But I think it captures some interesting answers to why questions. But in this talk, I'm not assuming any account of explanation, right? I want to work out an account of understanding that does not presuppose explanation. Now, you're quite right in saying that there are accounts of understanding that are very close to those accounts of explanation, right? Understanding how, right? They already, in some way, you may say they offer some notion of explanation, but that needs to be obviously worked out, right? And so that you can then differentiate the two. But that's a very good question.
Thanks. Jake, let's be very concise, please.
Yeah. So I'm sympathetic to a lot that's going on in here, but I sort of have a version of, I think, Dave's worry, which is something, but maybe I'll phrase it in my way and see if it sounds any different, more or less convincing. My intuition is that just when I am presented with the bare mathematics, I have not got any understanding whatsoever, unless one assumes that this is already a fitting model, right? So say contrary to fact, that the Lockov-Volterra equations were just totally spurious characterizations of Prey dynamics, and indeed of anything else, right? That's not a way the world could be, right? Because in order to know how a way the world could be, I would need to know something about the things that they are, right? But in order to know that this mathematical structure could reflect a way the world could be, I need an explanation of the applying the interpretation, right? And so it seems like there's no understanding before the interpretation happens, at least by my lens.
There is no, my point, that's exactly right? A piece of mathematics doesn't give you any understanding, right? Just the mathematics. So you need to have the interpretation bit. But the point is, you may have an interpretation bit that does not provide a full explanation, because you may interpret the mathematics in a way that doesn't give you any of the causal mechanisms, right? And that's what I'm saying. So for example, when I interpret the differential equations as standing for populational growth of predators and prey, right? So I'm giving now interpretation to those magnitudes, right? I haven't told you how these predators and prey behave, right? I didn't give you any of those things, right? But just by showing that, okay, this is a correlation among the growth of these two populations, now I have some understanding, namely an understanding about the way in which this population, the growth of the populations correlate, right? I think I do have an understanding. Do I have an explanation? I don't think I do. For that, I need to add an extra causal structure. But that goes even beyond, right? So if you think about the Dirac case, right? So he had the differential equation, and now he's interpreting. And he can, each interpretation, right, gives some understanding. One understanding says, well, that structure says nothing about the world. Ignore that portion of it. The other says, oh, look, there is this extra thing in the world, these holes in the space-time, right? Turns out that there isn't, right? Or another one, there is this new particle. So each one of these interpretations gives some understanding about how the world could be, right? Given the structure, right? Under each respective interpretation. They each offer some understanding, right? Even in cases that is non-factor, right? Even if there's nothing there, right? Such as holes in space-time, right? Sure, the world could have been that way, right? The world could also be a way in which there are no positrons, right? And then then we would not be talking about this thing, right, now, right? Because, well, it was one more case in which you have the wrong physical interpretation, right?
I have more to ask, but I'll...
No.
Okay, we'll talk more.
Yeah, thanks. I wonder if it's, this will connect up. I wonder if it's useful to have on the table the following kind of possibility. There could be something that's like a part of understanding, or something that's required for understanding, but which is on its own insufficient for understanding. And that, I'm sort of thinking, here's an example from understanding why literature. You gotta know that P to understand why P. You might think knowing that P is like a part of understanding why P, but on its own it gets you nowhere. On its own it doesn't get you any degree of understanding why P. It's kind of like a precondition, or you could call it a part, you could call it a precondition, either way. Now, is it a good thing to know that P, if what you want is to it's like, yeah, it gets you on the way. I mean, you're well on your way. You gotta meet the preconditions to get there. You gotta meet the necessary conditions to get there. You gotta have the parts to make the whole. But on its own, it doesn't get you any understanding. So there's sort of encourage that you and your critics could fight over this debunking explanation of the intuition that when you get the mathematical model alone, you've got some understanding. No, it's not that you've gotten any understanding yet. You've gotten something that's really good because it's a part of understanding. Maybe a necessary condition for understanding, or a precondition for understanding. But on its own, it doesn't get you any understanding. But it's easy to think it does because it's getting you closer. And it's easy to mistake something that gets you closer to understanding and is good vis-a-vis understanding with understanding itself. And I don't exactly know how you would resolve that dispute between you and your critics, but that kind of debunking explanation, I think, is what they should concede all that like the mathematical model is good as a route to understanding. They should concede that it's maybe even a part of understanding, maybe even a necessary part of understanding. They just want to insist that it's not understanding proper, and it does seem possible to sort of confuse something that is good because it's a part of a thing with the thing itself. Right. It's only going to get you the thing itself when combined with the other goodies.
Okay.
Presumably the explanatory goodies is what you're
right.
Is going to want
yeah.
to insist on.
No, this is an interesting point. I want to resist that knowing that is required for understanding, right? Because if you think about the case that Dirac had, right, he did not know anything, right? In fact, he didn't even know what was the possibilities. He was trying to figure out what was possible, right? So, and he was shooting in the dark at that point, right? So to say, okay, he needs to know that this is the case in order to understand, I think puts the cart before the horse, right?
Any other example of something that's necessary but not on its own sufficient would do. That was just an example that I thought.
Okay.
I thought everyone would agree to that because it was so obvious. obvious to me.
Well, maybe not, right?
But any example
Yeah.
where there's a part that's required, but on its own gets you none of the whole. That's the idea.
Yeah,
Is that
but
the
then-
mathematical model would be a part, but on its own gets you none of the thing.
Yeah, but in a way, it's just I have a hard time parsing parts. I'm not sure what is a part of an understanding, right? I have no grips on that, right? To really understand what you mean by a part of understanding here, right? I can understand the following, right? So in the examples I've been considering, the mathematical model is involved, and you cannot interpret a mathematical model unless you have the model, right? So that is correct. I agree with that, right? And the model alone doesn't give you the understanding because you need to interpret the model in some way to connect to the physical world, right? But there are many ways of doing that. Some of them might be empirically adequate, others may not be, right? And that's what I think that's what Dirac was doing, right? He was exploring possibilities, different ways of interpreting that mathematical model. I think each one of them gives some understanding, even those that do not give knowledge, right? I want to say he understood that the world could be such that there were holes in space-time, even though that's false, right? So, but then, you know, I'm non-factive about understanding, right? And I do think that, yeah, okay.
Thanks. I have two questions. The first question is probably related to the one that was just asked, so I'm not sure that it's worth spending too much time on it, because you just answered it. It was about, you know, I was again going to impersonate my wonder twin and tell you that I can so Carrie and Khalifa, and tell you that all of that talk is just proto-understanding. It's in a way to the real kind of understanding why, which requires explanation. So the TikTok move, right? Okay. So, but you just kind of answered that question. I think
I would like to resist.
Yeah.
I don't deny. There are cases in which explanation provides understanding, and Karim is right about that. But I don't think that has to be. That cannot be the whole story.
Right.
Otherwise, case like the Dirac case, you have to say, well, there's no understanding there.
That is proto-understanding.
Yeah. Yeah.
It might be a semantic question at this point, so it's not yet valuable. All right, so I want to talk about possibilities.
Mhm.
And I'm still struggling with it. So
Right.
it's one of the things that are still bothering me. So relatively recently, so I agree with you that the possible world is a bad idea. I don't think that your first argument against the possible world is really convincing. I think you could also explore possible worlds the way you explore logical possibilities.
Yeah, you
but-
can do impossible worlds, right,
Right.
if you want, right? That would be its own set of problems, right?
Right.
And I didn't add that because that had a different. So, but I do have worries about that as
Yeah.
well. So.
But I do agree that bringing the burden of possible worlds is not useful. It causes more trouble than it's worth. So now there's this distinction in the literature right now by Warning and Greenwing and off, right, about the epistemic possibilities and the objective possibilities.
Mhm.
And so I was wondering whether you had thought about that distinction and how that affects your account.
Right.
And then within the objective possibilities, you could think about various kinds, and they could be the logical possibilities, which is what you land on, and also the nomic possibilities, right? The possibilities that are consistent with the laws of nature, whatever
Right.
those are.
Yeah, good. Yeah, no, that's a great.
And so to me, when I'm thinking, and I'm still again struggling to figure out where I want to land on there. I
Right.
feel like in different contexts we're looking for different kinds of possibilities,
Yeah.
right? So when I think about superquantum correlations, so those are correlations that are possible according to relativity, but not possible according to quantum theory, and there's just weird things. So are those logical possibilities, given that they're maybe, but they're not nomic possibilities because they, inconsistent with what we take to be relatively close to the laws of nature?
Right.
On the other hand, when I look at what Makila Nassimi looks at, with the supersymmetric particles in colliders, here we look, those are scientists who are looking for particles we don't know exist yet, right? But they suspect they exist, so they go out there and they just hypothesize their possible properties and then find them. And so there it seems like the exploration of possibilities is nomic because it's depending on what, a little bit like Dirac was doing, is that depending on what we have in terms of mathematical formalism, which is the best representation we have to this at this point, for the whatever it is that we're trying to discover out there in the world.
Right.
So anyways, I'm still a bit confused about how to cast between, and then the whole epistemic possibilities also seems important, the one that depend on our current background knowledge, what is possible given what we know now.
Yeah.
So I'm a bit, I don't know what exactly, I know we explore possibilities, that I'm pretty convinced.
Yeah, they're great.
And I know it doesn't have to be explanatory.
Yeah.
And I know it doesn't have to be true. Okay, so we agree on all of that.
Exactly, yes, we do, yes.
The question is it the case that depending on the context, we're going to look at different kinds of possibilities?
Right.
That's probably the answer. I don't know.
Yeah.
What do you
Good.
think?
So here's the way I approach this. So I'm interested in the objective possibilities, right?
Okay.
I'm interested in the possibilities of the phenomena, right? And what is possible or not are going to be dictated by the properties of those things. I don't know what they are. I have to find out, right? So, and depending on what these properties are, and that include modal properties of the things that we are trying to understand, certain configurations will be possible, others are going to be ruled out, right? So, and I think all of those things is not epistemic. I'm interested in the objects, right? And
I think I agree with that.
yeah, so that's, and I think that's what Dirac was doing, right? He was interested in finding something in the world that would correspond to these the negative energy solutions, right? And so it's objective, though, right? Doesn't depend on him, right? But it depends on finding these connections, right, between a mathematical structure and some physically interpreted phenomena.
So logical or nomic?
Yeah. Okay. I'm an empiricist. I don't think the laws of nature exist, right? There are empirical regularities, right? They're fairly robust, fairly stable, but they could be otherwise. In fact, they're regularities that hold because other things hold. But these other things could be otherwise. So they also are not necessary. And you keep going like this, right? Of course, the phenomena we are dealing with are fairly stable, which gives us an illusion that they are necessary, but they're not, right? So the world of empiricism is a world of contingency, right? Everything is possible, right? So that's what's going on. So there are no necessities. The best you can get are conditional necessities. If certain things are the case, then sure, other things must be. But these certain things in the beginning, the antecedents, are themselves not necessary, right? So, and this goes for mathematics in the same way it goes for the sciences, right? Is every set well ordered? Well, it depends on the axiom of choice. If it's true, yes. If it's not, no, right? So I cannot say even in mathematics there are necessities, right? You say, oh no, but arithmetic, 2 + 2 = 4, right? Well, it is if you assume a certain conception of number, if you assume classical logic, then you do get. Change those things, you get inconsistent models of arithmetic, where things are very different. Well, so much for nomic necessities, right? I don't think they exist, right? Not in the philosophically robust sense that we are led to believe by philosophical conceptions of the sciences. I don't think that's a piece of philosophical fiction, right? Now, there are logical possibilities. And I think exploring the logical space is to explore what's possible or not, that different logics codify. The possibilities are already there. We are uncovering them and codifying with a logic that allows them to reason about those things, right? So if you want to reason about quantum objects, right, and with a certain understanding of them, right, then, well, it looks like distributivity needs to go through the window, right? So it's not consistent to keep classical logic with this unless you change non-relativistic quantum mechanics, right? Now, what is that possibility, right? Well, it's a possibility about quantum objects under a given quantum non-relativistic interpretation of them. And so I'm talking about these possibilities, right? It's logical in the sense that it ultimately boils down to what's compatible or not given the particularities of the domain in question. But what they are is an empirical matter, and we find out by exploring the possibilities, right? So I do think we have a primitive notion of possibility, right? It's the notion that gives us the notion of logical consequence, right? An argument is valid if and only if it's impossible for the premises to hold in the negation of the conclusion, right? So the very notion of consequence, the notion of logical consequence, is a modal notion. That's the notion that's primitive, right? So I think that's what's needed, right? But that notion, depending on the region of the logical space you're considering, is going to codify different things. So there'll be different logics as you explore and find things out, right? So that's the way I tend to think, right? So,
Stop it.
yeah, okay.
Yeah, because we are 1 hour late, so I supposed to be over 1 hour late. Then there is Andres and Steven. Please be very efficient.
Yes.
Beautiful as well.
Okay.
Thanks. I'm not sure this is a question or a comment. I guess it's more of a comment on the rhetoric of your presentation. You have the word modality in the title of your presentation. And, well, maybe I was expecting a much more special connection between modality and understanding. And the reason I say this is because if you think of any concept in science, if you think of laws, if you think of any universal generalization, there is modality involved. There is a space of possibilities. There is you have to think of all the possible cases and all the possible applications. So I was just wondering why you need to emphasize that the modal aspect of understanding, as opposed to what I think is a more direct contrast with other theories of understanding regarding the lack of explanations. So it's just a comment, just to.
Okay. Well, I do think that those various models that I was talking about give us understanding because they indicate possibilities, right? We understand what's possible given these models, right? So
Laws also give you lots of possibilities.
well, they don't exist, so I'm not sure what they give, right? So no, I'm serious, right? There are no such things, right? So there are regularities, but scientific practice unfolds that way, right? It's just that I think the practice is a practice guided towards understanding, right? More than towards explanation. We try to understand, right, what's possible given whatever is it that we're starting from, and given the phenomenon. Okay, we'll talk more.
So thanks very much, Otavio. So let me push back as well against the idea that there's understanding without explanation.
Okay.
So suppose I'm trying to explain why the wolf population is increasing. And one theory is that the fertility of the wolves is increasing. One theory is that the climate is making a difference.
Yeah.
And one theory is that the rabbit population is making a difference.
Yeah.
What the Lagrange equation will tell me is that it's not the climate, it's not the fertility, it's the rabbits. So that seems to be like, show me that the rabbit thing is a better explanation. So I don't know why that doesn't give me explanatory information.
Right, yeah.
Explanation.
No, look, it's very interesting because when you look at the way that the model is set up, it has a bunch of idealizations that exactly rule out some of those things, right? And it's allowed, the example I gave there was lynx, right? The lynx, they only eat the rabbit and nothing more, right? And the rabbits are only eaten by the lynx and no one else, right? And they don't die by any other causes, right? So otherwise the model don't work, right? So in a way, because of this idealization, you're already narrowing down some possibilities, right? So
you don't want to say that's an explanation.
That's right. So it's not, because you already built up a lot of things, right? So that you're ruling them out by fiat, right? So that the model can work, the idealized thing will work. So it's not really explaining, right?
That was great.
We have, no, we have 4 minutes. Anybody wants to ask?
Okay, I thought we were supposed to wrap up.
Okay, let's take Otavio.
All right, thank you.